the main overview of this was that we wanted to have a tutorial which showed how to go from vector datasets for land cover classification and actually convert them to like raster datasets or images that we can use to then train our model, right? Because we can't ingest vector data directly. So that is the main purpose of this notebook. And it also goes with the climate impact part and all. I think that you can go and read separately if you're interested. And so in terms of the background, the main thing that needs to be understood is vector data versus raster data, right? So let's say this is the real world, right? This is an image of the real world. It can be represented as like raster data. So it's like a 2D grid of images, of pixels. And each of the pixels will have a certain value. So let's say R represents like 10, pixel value 10 represents R. So all pixels with R will have like a 10 on them. And then S can be represented by like 15, etc. Right? So that is more, that is very similar to how you represent how we have images, right? Because each object here will have some RGB values or some sort of spectral representation, basically. The other way that we can represent this data is in the form of vectors. So this is by polygons, right? So here each polygon or line or geometric shape will be made up of a set of coordinates. So here you can see that river has been defined by like coordinate, let's say 150, 200, 100, 200, 200, 200, etc., etc. Right? So this is one way to represent like data. One of the advantages of using vector data is that it's more like it's easier to resize in a way, right? Since it's only geometric functions in a way. Whereas in the raster data, to resize this, you have to impute a lot of values and you have to calculate them using so let's say a pixel here, we'll have to calculate the value of it based on its neighbors by using any algorithm like nearest neighbors or some other algorithm. So these are the two main differences between the data. One other thing to keep in mind is that with the raster representation here, each of these pixels will also have a geospatial coordinate attached to it for satellite imagery. So let's say we are in a coordinate reference system, which is, our normal Euclidean plane. So this pixel would be 1, 1, this pixel would be 2, 1, etc., etc. But you can also represent these in a different coordinate reference system, right? So this could be latitude value 1, latitude value 2, longitude value 1, longitude value 2. And that's how you can represent them and then place them into the real world and relate them to the actual real world itself. And so the main thing about CRS that you need to keep in mind is that when you are doing functions, combining rasters and vectors, just make sure to have the same CRS. The CRS that we select won't really be like a very big hot topic or debate of topic of discussion right now. We'll just pick one CRS and go with it. So just keep in mind that we want to keep everything in the same CRS, right? Just that is the main thing that you need to keep in mind. Is everyone clear on that? For the raster and vector part, that's like the main thing. Okay, if everyone is good on that, I'll go to the next part. So what we did here was we had a Sentinel-2 image. So it has 12 bands. Each of these bands can represent different things. So for example, this is like an aerosol band, so it'll represent like the aerosol level. This is the blue band, green band, red band. And yeah, you have the near infrared, you have the vegetation red edge band, you have multiple bands, right? All of these bands are selected from like a spectrum of they have different wavelengths that you can see here, different central wavelengths. And also they can have different resolutions. So you'll see that the blue, red, green band, they have 10-meter resolution, whereas the coastal aerosol band has 60-meter, and yeah, it varies for the other bands as well. So this resolution basically represents what one pixel will mean, right? So you can take it to be as if the blue band has a resolution of 10 meters, then that means each pixel will be 10 meters by 10 meters. That is the area that it will be representing. What we also want to keep in mind is that when we're dealing with imagery, we want to harmonize them to the same resolution. So one of the okay, it could be that we want to keep them in different resolutions. If they are very far apart, let's say if you have a 10-meter band and a 100-meter band, it does not make sense to combine them a lot of the times. But let's say in our case, let's keep it simple. We want to harmonize them and we want to bring them to the same resolution. The reason for that is after this, if we bring everything to the same resolution, we can treat it as one single image with like n number of bands. So in this case, 12 bands, and that makes things a lot easier. And these are just some applications as well as some information on co-registration. Co-registration is one of the steps that you take to harmonize the data. This is just explaining semantic segmentation. So semantic segmentation is just taking an image, putting it into a machine learning model. The goal of the machine learning model is to give you an output where each pixel represents like a particular class. So in this case, it is represented by like the model is finding person, purse, plants, grass, etc. Here it's represented as single class numbers, but from the machine learning model, you get like probability values for each class, and then you decide which one is the correct one. So the whole point of this is to create a data set for semantic segmentation, land cover data set for semantic segmentation, which is why all you need to know about segmentation is this right now, that this is our target use case. So how do we actually go about this? So the first part is just installing some of the required libraries. And after that, these are our imports for different things. And we also download some of the data. So we stored some test GeoJSON as well as some of the imagery. So we already downloaded and preprocessed some imagery and stored it on Google Drive. So all this does is downloaded. And this is the JSON of our area of interest. So this represents like a single box, since you can see that it has, so it says 5 points, but the first and the last point will be the same. The reason for that is that you want it to form a closed shape, right? So 1, 2, 3, 4, and 5 again to the same shape back again. So since it's a polygon, you want it to be closed. And yeah, so these are a bunch of things. Okay, yeah, to explain the GeoJSON a bit more. So it is a feature collection. So it can have one single GeoJSON can have multiple features in it. Each feature can be of a different type. So the feature that we're representing here is a polygon. We also have an key for representing some additional properties. If you want to, this could be the CRS, or it could also represent like, for example, we saw in the earlier notebook, we had something for like top class. You could represent this row in the properties part of the polygon in a GeoJSON. And sorry. And yeah, so the geometry itself, it contains the coordinates. And what we'll do is similar to what we did in the earlier notebook. We load the GeoJSON, and this is what our GeoJSON represents right now. It's a bounding box. And for reference, it is from Paris. So like the middle of Paris. And this is one way to download Sentinel-2 imagery with like a GUI, basically. So you can follow this if you want to get Sentinel-2 imagery using the GUI. The other way is you can use Microsoft Planetary Computer, or like a bunch of different APIs exist. You can try and look into that if you want. So what we did after that is, I think we just downloaded the Sentinel-2 imagery. And yeah, these are the different variables that we had. So you saw that we had 12 bands in total. But to keep it simple for this tutorial, we only chose the blue, green, and red band in addition to the SCL. So what is the SCL? So the SCL is meant to, how do I move this bar around? Okay. SCL. So the SCL is like a land cover classification. So for each pixel, they give us like some sort of land cover classification, whether it's no data, saturated, effective, clouds, water, just a very broad land cover classification. Uh, it can be good, but sometimes it can be very bad for clouds, especially. But yeah, this is what we'll use to detect clouds in the image for now. This is what we'll use our ground truth clouds. And as mentioned in the earlier notebook, we have some additional attributes like valid percentage of pixels not cloudy, the date string itself, the tile name. So this is a reference to the actual tile that we're downloading. Just to explain tiles really quickly. So satellite images are stored in shapes are stored in tiles like this. So let's say this is tile number 1. This will be tile number 2 right next to it. Tile number 3. Tile number 4.
Are you drawing?
Yeah.
Oh,
As
on
in
the
on the mirror board.
annotations?
What do
Oh,
you mean?
you're not oh, on the mirror board. Okay, thank you.
Yeah.
I'll go to the mirror board. Hold on.
Yeah. So yeah, you for everyone else, is it visible in my screen?
It's not in the screen capture, but we can go.
What
Oh,
about
there.
no?
No,
I
now
think
it is.
I paused the share by mistake. Sorry.
Oh,
Okay.
okay.
My so I just go. Okay. So imagine this is one tile of satellite imagery, right? This is tile number 2. Um, this is tile number 3, and this is tile number 4, right? So satellite imagery is stored in the form of tiles. So these can be very large, and their size really depends on the satellite itself. But the whole idea is that it's stored into tile data. It's not like all of the satellite imagery is not stored into one single file, because that would not be very efficient to download and search. So when we actually want to download some area, what we do is, let's say this is our area of interest, right? I'll just make this hollow, and yeah. So this is our area of interest. So there can be 2 or 3 different cases or when we are querying with an area of interest. The simplest case is that it falls into one single tile, right? Another case is that it falls into 2. Another case is that it falls into 4 and 3, etc., right? Actually, 3 won't be possible. But yeah, it falls into 4. So what we need to do is, first we need to see the area of overlap of this tile with the different the area of overlap of our AOI itself with these different image tiles, right? And so, for example, in this case, what we might get away is just taking this top left tile. We take this top left tile and we only get the information for that. And this all of this information will be clipped off, or it will be black. Another approach is that we download all 4 of the images and then we mosaic them together, and we get only the area that is, we get the area which is present in our AY from all of these different tiles. So this is how satellite imagery is stored, and this is how you will be querying the data. Usually it is easier to have a small AOI so that it fits into one single tile, and you can just pull the data from a single tile, and you don't have to go about the process of downloading like 4 images and then combining them together and then clipping all of it, because that's a lot of additional work. Also a lot of additional like download and compute, because these tiles can weigh, depending on the satellite, it can weigh from like 1 GB to 10 GB. It really varies. Okay, so getting back to the tutorial itself. So what we did is we downloaded an AOI already from our SpaceSense downloader. And so yeah, this is just explaining the different coordinates, data variables, attributes, what they mean. And this is already something that I think we've gone through. Yeah.
Oh,
Uh,
I have a question.
mhm.
Could you explain what mosaicing means?
So mosaicing in this case would basically mean that you take, you create a mosaic of multiple tiles to fill in your required AOI. Yeah, that's it.
Okay, so you fetch multiple tiles until you can reconstruct the AOI.
Yes.
Okay.
But it can get complicated because we usually, like, I think where we basically just, at SpaceSense at least, uh, we set a smaller AOI size to prevent the mosaicing part. I did not work on the mosaicing part directly, but there were a lot of complications with it and getting it to work properly. So I think we try to avoid that as much as possible. And yeah, so these are just explanations of the different attributes, data variables, and coordinates that we see with X-ray. And what we do is we define some functions for just getting the RGB image from our X-ray file, clipping it to a certain value. And yeah, we just get the RGB band separately first, and we plot them along with the SCL band. And we also plot the RGB image itself. So this is Paris, and you can see that it has a lot of clouds. So since this is a very large image, let's say we want to do like road detection, right? It does not make sense to do road detection on this whole huge image at once, uh, because yeah, in terms of compute, it would be very heavy for a machine learning model. So what we want to do is we want to actually, wait, I'll get to that part later. What I'll do now is we have this image, we'll get the corresponding ground truth for it, as in what pixel contains like roads, what pixel contains water, what pixel contains buildings, and then we'll get to the part of creating an ML data set for it. But okay, the next step is, since we have this RGB image, how do we actually match the vector ground truth that we have to this image, right? So what we do is also we get the bounds of this image using like Shapely, which is another geospatial library, and like just X-ray functions. And we create a geodata frame for it in the 4326 CRS, which is what we want to rasterize our ground truth into. So for this tutorial, we use the European Urban Atlas, which contains, yeah, I think it's available for like 2018, 2019, 2021. But yeah, it tries to map the land use and land cover maps for like different parts of Europe, but mainly around cities. And what we did is we used this and we read this into using GeoPandas again. And what we see is that, again, similar to like a pandas table, we have different columns, which is the country, FUA name, FUA code. So these are just codes for the location itself and which area it belongs to. And we have different classes. We have the date it was produced or provided, I'm not sure. We have an identifier, parameter, area, etc. And for each of them, we have a corresponding geometry. So this geometry here is represented by multi-polygons, which is basically a collection of polygons. And what we do is after that we discard a lot of the columns that we don't need. We only need the class column and the geometry column here. These are the different classes that are present within this data set. So it's like 26 classes. And we also see that it has a lot of different categorizations for the same thing. So for urban fabric, you have discontinuous urban fabric, you have medium density, you have high density, etc., etc. And this is what the the polygon count looks like for this GeoPandas data frame. So you can see that we have a lot of urban fabric, dense urban fabric, which makes sense in Paris. The next thing that we do is we define like a function to yeah, just load this in on a on an image. And this is what the black thing, the black box is our actual area of interest. So the polygon that we got from our image. So that is the area our image covers. Whereas the urban atlas, that's the area that the whole of it covers. And you see that there is a lot of useless information that we don't really need. What we need is everything inside this polygon, nothing outside of it. So this is the whole dataset creation methodology as a chart, where we take the vector land cover data, which is the European Urban Atlas. We load the vector data as a geodata frame. We change the CRS to match the CRS of the imagery, which is 4326. We find the intersecting polygons between the S2 and vector data. For doing that, we also need to download the S2 AOIs. We need to download the images, and from that we get the S2 bounding polygon. Using this, we create a segmentation mask from the actual intersection of these polygons. So basically this part. So we want to create a mask out of this area within the black box. And for the S2 image itself, we want to create like a depth-wise data stack of RGB, CL, and the mask itself. So we'll get into how we create the segmentation mask from these intersecting polygons. After that, so this process is basically rasterization. So when we go from here to here. After that, we create n by n patches from the data. So the reason for creating n by n patches is that the image above, let's say it's like 1000 by 1000. It's very hard to put into a machine learning model because of it being very big, and you need a lot of compute if you want to work with images of that size. In addition to that, you also don't want to put this whole image into a model because a lot of it contains clouds. And those regions aren't really suitable to put into a machine learning model because you will get erroneous output, or you will basically get erroneous output because of the clouds. Another thing is that in a lot of cases, what you want to do is you want to control the geospatial context that a model is getting. So let's say you want to create so land cover might not be the best example for it, but let's say you're working with crop type detection, right? So let's just go to crop type detection. So this is what we were looking at earlier. This is crop type. So let's say you're working on crop type detection and you want to train a classification model. So a classification model will have one output for one image. Unlike a segmentation model, it does not have output for each of these pixels. Whereas if I have a single image, it will either say barley, corn, fodder, or some other class. In that case, it makes no sense to give this whole image. And what you would want to do is you would want to make it so that the image size itself, the value of n, is so that it covers only a single field of crops rather than multiple fields. Because if it's covering multiple fields, then you're giving erroneous information to the model, and it's hard for the model to determine which field you wanted to predict for, right? So a lot of the times, geospatial context can also matter in terms of what information you actually want to feed into the model and what your use cases. But yeah, so I'll just go back to the flow chart. So yeah, we divide the image into n by n patches from the data stack. As I mentioned above, some of the areas, they had like cloud cover in them, right? So what we want to do is we want to check individual patches of data for cloud cover and other data quality parameters such as missing data like NaN. And we want to store all of this information as metadata. And we want to discard or invalid data according to user specifications. So this is dependent on the problem that is being tackled. For example, for this land cover here, no data and cloud cover are the two major things which are required to discard data. Another one could be, let's say you only want to train on images of roads, right? So in this case, what you can do is you can also store the class-wise information containing, so the class-wise information can contain, okay, for each patch, what is our class distribution? So how many pixels are road, how many pixels are buildings, etc., etc. So you can also discard images which don't have a lot of road, right? You might want to discard them from your dataset. So that's just a hypothetical example of what you can put into data validity settings, but it really does depend on your use case. And after that, after you have discarded the invalid data, we save the images as a netcdf file and a PNG, and we save the metadata along with it. So in this case, since we were saving the images, so in this tutorial, we were just mainly saving the images as RGB, or we were using the RGB images. The reason for that was that it's just easier to interact with. But one of the downsides of it is that you can't store segmentation masks directly, whereas in netcdfs you can. So if you're storing your data as a PNG, you can't just start another channel. So for that, we stored the data in like Cocoa annotation format, which is just annotation format, which again represents the data as polygons, like vector files for image masks. But these are not georeference. So these you can think of as just pixel values.
And for
So
those, sorry to interrupt, and for those that took my 175 class, Cocoa is one of those data sets that are considered benchmark data sets in computer vision. And so the benefit of putting your segmentation masks in Cocoa annotation format is that a lot of people in the computer vision community are already familiar with the Cocoa annotation format. And so that's really like if you're curious about that, you can always look up Cocoa and for semantic segmentation. The other thing I wanted to note, just to keep on track on time, is that we do have about an hour left. So I want to make sure that we have ample time for the flowchart that you also created. So just putting it out there.
Yeah. So after this, so this is our whole pipeline, and we'll see how to do the part of the creating the ground truth, because we already looked at the part of creating the actual Sentinel-2 imagery. So to create the ground truth itself, what we do is first we find intersections between the geo package and our actual area of interest. So from the image, we got a bounding box, right? So what we do is we find overlapping polygons. Just to keep in mind that all of this, like this notebook, it sort of goes through the steps in a naive way. There are like tools that already do this for you, tools and libraries which do this for you, but this just goes through it in a very naive way to try and explain the main steps. So what we do is for each of the polygons in our geodata frame, we check if it overlaps with our image or not. And we can just do this by using like the intersects function of our polygon itself. So this is a function to do that, and we apply it to our geodata frame. So our European Open Atlas, we apply it to that. And after that, we get only the intersecting polygons, and this is what we're left with, right? So a whole lot of data just got deleted, which is very good because it makes everything very light compared to earlier. But we still see that some areas. Why is the extent of our plot? Why is our plotting this like light green thing? Right. So what we see that this like represents I think roads. Yeah. So this represents like roads and associated land. And all of this is represented as like one large polygon or multiple large polygons, which also run through our AOI, but also run like into the whole of area of the actual European Open Atlas. So what we want to do is we want to delete these areas. So the next thing that we'll do is we find intersections with the query polygon. So we take the European Open Atlas for each of the polygons in it. We take our image bounding box or our image query polygon, and we find the intersection between them. The intersection will only keep the area which is within the bounding box and discard any of the area of the polygon which lies outside the bounding box. So once we do that, this is what we get. So these are all the polygons that lie within our black bounding box that you see here. and they represent different things. This is the water, these are buildings, like there will be roads. So what we want to do next is we want to take these and convert them to a format where each pixel of the image corresponds to one pixel in the ground truth, right? So we do that by creating a segmentation mask. And the way we create it here is, again, this was a very manual process where I think what we do is we go through first of all, we dissolve the polygon, the data frame. By dissolving, what it does is that it's combining so for example, if uh, these two are different polygons for class, it combines it into one. So each class will end up with a single polygon. The reason for doing this is to reduce the number of computations for our next step. And what we do in the next step is we use the image and we go through the image. For the image, we query it or clip it using the polygon, like each polygon in our European Urban Atlas. And then we fill in that area which is left with the corresponding color. So that is how it ends up creating the segmentation mask. Again, this is a very naive way to go about things, and there are better ways to go about it. And there are also tools and libraries to do this. But yeah, this is just for like one very basic algorithm that you can use. One of the libraries that are very useful for this is called GeoCube, and I think we will end up using the library in our project. One of the other things that I wanted to mention is that rasterizing our data, our vector, and then combining it with our other raster satellite imagery the whole process is called data fusion, because you're fusing data of different modalities. And yeah, this is the image that we get, which seems to match the dimensions of our RGB image. So this is the image of a shape of our original image, which is 700 by 1250, and the shape of the mask is 700 by 1250. So yeah, the next step is creating n by n patches of data, right? So we want to divide this into smaller pieces. So we define a function to do that really quickly to create splits. And then one other thing to keep in mind is that this value might not be directly divisible by like your value of n cross n. So let's say it's 128 by 128. It might not necessarily be divisible. So what you can do is you can just mirror the image at that point to get it to a value where it is divisible. And that is what is done. We calculate the padding that is required and we add it to the image before we do the actual splitting. And yeah, so this parameter was set as 64 here. And after splitting, this is one sample chunk of imagery that we see. So this is the image on the left and the mask on the right. And then the next thing is, as I mentioned above, we need to check each of these smaller images for data quality, right? So we define functions for checking the cloud cover and checking the like no data nan percentage and no data percentage. So no data, as I showed you with the SCL band, it can be represented as no data there, or it can just be nan pixels. So these are the two we need to check for. And this is just a for loop to go through all of the splits and get all of these data validity statistics. On top of this, we also store them into like an information data frame. The reason for this information data frame is that it provides you a very easy way of, first of all, looking at the data and also discarding data. You can plot it very easily for like an EDA, and like filtering is like you're just pandas filtering. You can select images which have cloud cover less than 20% very easily. So this is something that we, in my opinion, should be created for each data set that we create, because sure, here it is being used to filter for data before we save it. But another use case for this information data frame is storing a lot of information and subsampling the data set later on. So what I mean by that is, let's say let's take annual migration. So for annual migration, we might end up creating a data set which has turtles, dolphins, and whales, let's say. But we want to train individual models at the end of the day. I'm talking about a hypothetical case, by the way. We want to train individual models for each of these three classes, but we'll create the same data set for them, right? So to subsample it very easily at the time of training and not having to go through all of the images again, what you do is you just take this data frame, you see which images have what class, and you're good to go. So it provides a very easy way of verifying the data. Yeah.
Sorry to interrupt. There's a question in the chat. So how do we determine how big the n by n patches will be?
So the n by n patches, it really depends on your use case. So as I mentioned earlier, for n by n, it can either be restrained by like the compute capability that you have. The other thing is it can be restricted by like the spatial context. So in some cases, you might not want to feed the machine learning model like multiple. So I'm taking the case of crop segmentation, for example. So here, all of these represent different crop fields. If we want to train a model for crop classification using a single image, so for each image, there will be one output. It does not make sense to show it multiple fields, right? Because then you're giving it multiple contexts of what to predict on. So in that case, you might want to restrict your spatial context. So that is one more reason why you might want to select like a smaller size or a different size. Whereas to give you another example of the same thing, if you want to segment something like forests, or not forests, trees are pretty easy to detect, but roads, for example, it might make sense to have larger context, like larger image context, because you can see more of the road, and it might be easier for the model. So it can go both ways in terms of adding spatial context or reducing it to your needs. And just to continue from that, yeah, so this is just a function to plot some of the images with their different data validity statistics, the RGB image, the SCL image, and the European Open Atlas mask. So this has a very low cloudy percentage. And yeah, so it's different images with different values. The other thing that we have to keep in mind is that the cloud mask that we get from Sentinel-2 isn't always very good. So a lot of the times, like bad data can still leak through. And yeah, so we set our cloud cover limit as 10 and RGB NaN limit as 0. So what this means is that all images with cloud cover above 10% will be discarded, and all images with a NaN percentage more than 1 will be discarded. So we see that lots of images were dropped, right? We dropped 112 images out of 220. And just to show you which images were dropped, so the above this was just functions to plot this image. And so here you can see that the image at the back, that is our original large image, whereas these smaller splits that we've created is what we're storing and checking for data validity. So all of the red ones have been dropped. This can be due to, clouds, cloud shadows, NaN data, or some additional, actually those are the only two things that we use. So it can be due to clouds, cloud shadows, or NaN data. In addition to this, you see that some things still got through. And the reason for that is that Sentinel-2 cloud mask is from the SCL band isn't always very good. So what we do now is we save the data set as a multispectral data set. So in this form, we're storing it as netcdf images. So that is one way to store the data set. And in this case, you just add the mask as an additional data variable to your data cube, and you store that. So you don't have to do anything to the mask in this case. When we need to store the data to as an RGB dataset, what we want to do is we want to, yeah, as I mentioned above, we need to convert it to a format, to the COCO format, right? So I think these are just functions to, yeah, to convert the images to COCO format. No, these are just the image functions to write the images themselves. And yeah, after this, we store the data in COCO format. I won't get into this much right now, but in terms of this is the main structure of the JSON or the dictionary that we store the data in. So it contains info, licenses. Within the images, there is another dictionary which stores your data. Under images, you also have different subcategories of metadata for each image. These are all of the categories that exist in your data set, and then annotations contains the actual masks of the images. So these are just functions to create these different dictionaries and save them. For generating mask annotations, we go through each image. Within each image, we go through each mask. Within each mask, we go through each class, and then within each class, we do a contour detection, and these contours then can be converted to like COCO annotations. So, for example, when I said that we go through different classes, right, for each of these masks. So these are the different classes in this particular mask, and each of them will then we apply a contour detection to. So contour detection, it will basically detect these different polygons. So in this case, there will be multiple polygons. In this case, there will be 2, 3, etc. So that is what we do. And after that, we also have to encode it into a run length encoding to actually save the data with COCO. And we also have like same way you also need the decoder part later on when you're training the model. So yeah, all this part does is create the COCO annotations. And I won't get into this part a lot because it's something that you can go through yourself as well. And after that, we just trained a segmentation model using a created data set. So this is just the data loader. So all this does is it for each image in our information data frame, it will load the corresponding COCO annotations for it. And from that, it will then generate the output image as well as the mask in raster format. So yeah, this is the model input, this is the ground truth, and this is what we feed into our UNet. So this is a UNet model, which is like the standard for segmentation. And yeah, this is just an explanation of the UNet part. For now, I don't need to get into this a lot, right?
No, I think you're good.
Okay.
Because this is specific to segmentation, and we might not do the segmentation task immediately.
Yeah. And yeah, so all this does is it creates a unit. After that, we already created the data loader. This is the input shape of our model. This is the output shape. And yeah, we define the model trainings and metrics, and we train and visualize some results. So again, this model was trained on like 80 images, 90 images, so the quality isn't going to be great, but that was not really the point of the tutorial. It was more of how do we create the data set for it. So yeah, these are what we get as like input, ground truth, and prediction. And the reason why it's so pixelated is because the images are very small. They're like 64 by 64, but they're being displayed on like a larger grid. And yeah, after that, I think this is just some additional information and discussion regarding the results, which I would say, I think, okay, let me just read through them really quickly and see if any of these are important to discuss right now. Okay, yeah, geographical variance is one thing that we need to keep in mind. So unlike like let's say like a car in France and a car in US will look very similar. But when we're looking at geospatial problems, a lot of the times this can vary. Like a farm in France will look very different from a farm in US. So geographical variance is something that needs to be kept in mind during training, as well as when you're making predictions, because a model that is trained on like France might not do very well on US. On top of this, there can also be seasonal variance. So if you train a model only on like winter time, it might not do very well during like summer or like rainy season, just due to the differences in the spectral parts, as well as differences in vegetation. For example, during winters, your trees might not have a lot of leaves, but during summers and spring, you'll have like lots of leaves on the trees. So this is a pretty big point for agri-tech and agricultural applications in particular. Cloud cover is one thing that we discussed. I think data quality checks. So another thing is combining classes. So we saw above that we had like 26 classes, right? Which might not really make sense for the machine learning task. It might make sense from a survey and a data storage part perspective, but not really from a machine learning perspective. So in that case, we might want to combine some classes. For example, we had like 5 classes for urban fabric. These can be combined into one class. We had 3 or 4 classes for like fields. These can be combined into one. Class distribution can be class distribution is one more thing that you need to keep consistent between your train, test, and validation splits. And these can be based like on a couple of things. I think we'll get to that later on. Class imbalance is one more issue that is very prevalent in geospatial data. The reason for that is that it is like an inherent issue. You will not find as many images of airports as you will for trees, just due to the fact that there are so many trees compared to airports, right? So there will always be an issue of class imbalance, and there are different ways to manage it. And we'll look at those, I think, later on as well. So we have some limitations with like scaling and optimization. So this was like a very naive thing. It won't really work with very large data sets. I think I don't even remember what this was. I think this was just about adding different bands, which could be helpful for our analysis. For example, like NIR, the near infrared band, is very useful for like vegetation and detecting that, or finding like different levels of vegetation, for example. And manual checking, I think, is just for just errors with our base data set due to the like factors such as cloud cover, and also there are issues in ground truth data sets a lot of the times in geospatial data, just due to the fact that it can change, right? Like during a near, a building can just simply like disappear. Like you might make something else instead of it, right? So that is also one additional thing that happens very often.